Welcome to the Simple MPC Workshop. In this workshop, we'll go through a number of exercises that demonstrate how MPC can be used to maximize throughput of a process unit when there are a number of operating constraints on the process operation. To demonstrate this, we'll be using a dynamic simulation of a batch reactor in which we wish to maximize the feed rate to that within pressure and temperature constraints. In the first part of our exercise, we'll increase the feed rate up to the point where we are at the temperature constraint. We'll then introduce a disturbance which reduces the cooling capacity and then see how MPC handles that. We'll then increase the cooling capacity and observe the response to that. We will then introduce an increase in feed rate and observe how the constraint on pressure controls impacts automatically the actual throughput of the unit. We'll then, under that constraint condition, introduce a second constraint of reduced cooling capacity to see how that is handled. For this exercise, then, we have a batch reactor in which initial charge has been made, and then we're adding feed, which is then reacting with material. We have a split range control of heating and cooling that MPC is adjusting, and then feed rate, the flow to the unit. The constraint, the temperature control is a constraint and also a control parameter. The pressure is an operating constraint on the unit. So as more reaction is going on, more gas is evolved and the pressure is increased. This is the module showing simple MPC implemented as a function block where we're measuring the pressure and temperature as control and constraint inputs. The output is going to a splitter block that goes to heating and cooling valve, and the other output goes and determines the set point of the flow to the unit in terms of the flow set point of that flow controller. The online interface to the operator for simple MPC is shown here. There are controls where simply by clicking on MPC, the downstream blocks are automatically put into cascade mode. MPC can be run in automatic or auto, manual or automatic control. Based on the configuration of the MPC block, then automatically the control parameters are shown up as small faceplates here. Also, our manipulated outputs are shown as small faceplates. So the output to our splitter block and the output to the flow control, and our constraint on operation, the pressure, is also shown here. So to demonstrate the capability of MPC, we're running at target on the flow to the unit. We're going to increase that and observe the response of the process. As we see in the trend area, the set point change is noted, and then the flow rate is shown in blue coming up. Its impact on pressure is shown over in the down below. The green area is the future prediction of where the parameter is going to go. As we increase throughput, we notice that we have to add more and more cooling. That is the split range controller output. We have to demand more cooling. As we increase the flow rate to the unit further, we eventually get to the point where the need for cooling is at maximum cooling capacity. So the split range output is at 0, which means maximum cooling flow. The cooling valve is fully open, the heating valve is closed. And so we're now operating at the capacity of the unit. We really can't stand to have any more throughput. There's no cooling capacity, and in this kind of an application, the temperature could continue going if we exceed the capacity of the cooling unit. So to demonstrate what happens when we have changes in the process, say the cooling capacity is decreased, maybe the cooling media has decreased in temperature, we introduce a disturbance. And we see that immediately as a result of the decreased capacity of cooling, the temperature has gone up. To keep the temperature at set point, MPC is automatically reducing the flow rate below the operator target. And this is necessary to keep us from exceeding the temperature constraint and maintain temperature at the desired operating point. So as we decrease the flow, then the cooling capacity is enough to maintain our temperature. So we reduce the flow rate only enough to keep us right at the ragged edge of our temperature control, keep us right on temperature set point. So we're maximizing the throughput under this operating condition of our plant. So under this condition, if the cooling capacity suddenly becomes greater and the temperature drops as is shown here, then automatically MPC raises the feed rate back up to what the operator requested because now there's plenty of cooling capacity to achieve the target set point. As it raises that up, then the temperature control done by MPC automatically regulates the cooling valve to get us right at temperature set point. As we saw the throughput come back up, we noticed that our pressure now is at a higher value. We're still within the constraint that's noted in the little faceplate for the pressure by the arrow. So we're still below the pressure constraint, but we're getting pretty close to it here at this particular throughput of the unit. To demonstrate the pressure constraint, we'll increase the throughput target. And when we do that, we notice that the flow is increased to the unit, but as the pressure starts to approach the pressure constraint, the throughput is maintained at a value below the operator target, just at the point where the pressure is going to be right at the pressure constraint. So we're maximizing the throughput of our unit within the capacity set by these operating constraints, the pressure of the unit. So we're getting the most through without violating our pressure constraint. Now, oftentimes an operator is really reluctant to be operating a unit at the operating constraint because if anything happens that disturbs the process, then that could cause a constraint violation. In this particular case, what we'll show is that where we're operating at the pressure constraint, we'll introduce another disturbance in our cooling capacity to reduce the cooling capacity. So our temperature immediately shoots up because we have lost cooling capacity. As a result, the MPC is going to automatically reduce the throughput of the unit. So here's a case where we were under pressure constraint, but due to a process disturbance, we're now operating under the cooling capacity constraint. And we are reducing throughput to get to the point where we can maintain our temperature set point given the constraint on the cooling capacity. So this demonstrates that under a variety of operating conditions, we can use MPC to maximize throughput, safely maintaining the unit always within its operating constraint, and yet maximizing to take maximum advantage of the capability of the equipment. I hope this exercise has been helpful to you in understanding how MPC is used to maximize throughput. The pusher capability of small MPC can be quite effective on small units in terms of optimizing throughput.